Okay, in this video here, what we're going to do is talk about a lot of the predefined data types that are available to you in the C# language. Now, there's quite a few of them, so this video may get a little bit lengthy. Now, before we start talking about all of the predefined types that are available, the first thing I'd like to do is point out something that I've already said several times. Our predefined types, well actually not even just our predefined types, but types in general, data types break up into two different categories. Now we're not going to be talking about these two categories in depth in this video, we're going to do it in the next video, but I do want to present the very basics of it for the simple fact that I'm going to divide all of these predefined types up into these two categories when I present them to you here. So what two type categories do we have? Well, we have value, and we have reference. Ooh. What does this mean? Well, actually, it's quite simple. Let's go ahead and start out with a very simple value data type. So, let's say I have an integer, it's called I, and I'm going to put the value 5 in it. Now, what does this translate to in memory? Well, in its most basic form, I have a little bit of memory set aside that basically has been labeled I, and the value 5 is put in it. Notice how I said the value 5. 5 is actually in it because that is what I assigned to it right here. Now, reference type is a bit different. Reference type means that we are basically creating an object. So if I was to do, let me think. I know what we'll do is we'll pick on Canon. Remember how we had game items? So what if I was to create a game item? Once again, remember, this is my type. Now, what is its name going to be? Let's say player. And how do we do it? Remember, we said equals new game item. Now, in Volume 1, we talked about this quite a bit, so this should be very familiar to you. So there you go. Now, by doing this, we are actually creating a new game item object, and a reference to it is being stored in player. So what does this look like in memory? Well, basically, here's our little piece of memory that's set up. This memory has been labeled as player. But instead of seeing the actual object inside this variable, we see an address inside this player variable. This address is really just a reference to another memory location where we'll find our actual player object. So, in this case, we saw a value. In this case, if we were to use a can opener and open up that variable, what will we see? We see a reference. Okay? An address pointing to another memory location. So, value and reference. All right, let's go and wipe all that out. So why is that important? Well, first, let's go ahead and talk about our predefined value data types. Now, before we do that, Logan, let's make this a little bit more interesting. Let's introduce them to the lowest level piece of information they can store. What is it?
A bit.
A bit. That's basically a 1 or a 0. So let's draw. Here's a nice little memory location. This is a bit. Ooh. And it can hold rather a 1 or a 0. That's it. Now, how many bits make up a byte? Well, we have 8 bits equals 1 byte. Now, I know you're probably thinking, why are you, I don't get it. Why are you showing me this stuff? Well, we're about to start dealing with variables, and when dealing with variables, talking about data types, now what are we dealing with? We're dealing with memory and how much information can be held within that memory based on the data type we're working with. And this is going to become very important because in a second, when I start writing all these predefined value types out, I'm going to show you the ranges, and hopefully by giving you this little demonstration here with bits and bytes, it's going to make sense as to how much information these variables can hold. So let's go ahead and draw this out real quick. So if I do this, and where's my shift button so I can try to make this straight? I guess that's pretty straight. And then I make another one like that. And then I make my not so straight. All right, so 1, 2, these are bits, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 8 bits all grouped together, and that makes up 1 byte. Now, let's get a little bit fancier. Let's draw some more stuff out here. Let's do a little bit of exponent stuff, like 2 to the 0. Anytime something is to the 0 power, it is a value of 1. So let's just put that down here. So that means that is a value of 1. Now, how about 2 to the 1? That's just going to be 2. What about 2 to the 2? 2 times 2 would be 4. How about 2 to the 3? Well, 4 times 2 is 8. All right. Wait a minute. Buzz, why are you showing this to me again? Again, when I show you these ranges, by having an understanding of what's taken place with this byte, it's going to make a lot more sense. All right, so 2 to the 4th. See, now you just got quiet and you're trusting me, I hope. All right, so 8. So now we're going to go times 2 is going to be 16. So 2 to the 5th. So this is going to be 32. 2 to the 6th. So this is going to be 64. And finally, 2 to the 7th. And this is going to be 128. So let me do this just to make it a little bit clearer while everybody's jotting these notes down if they don't understand working with binary here. All right. These are like dotted lines. I promise not to add any extra confusion into the entire mess that I am presenting on the whiteboard. All right, fantastic. Now, as we said inside a bit, all we can do is hold the value 1 and 0. That's it. So I can come up with numbers by simply adding these things together. For instance, let's stipulate that all of these, let me see if I can pull a pointer up here, that all of these boxes right here are all set to 0 with the exception of this last box. If it had a 1 in it, what we need to do is add up all of the numbers down here that have a 1 in it to get the total value that's being stored in this particular byte. So if I had a 1 right here, all of these would add to 0. This guy would add to 1. So all zeros with a 1 at the end is truly the value 1. Right, Logan?
Right.
Now, let's say I wanted to represent the value 2. I'd set all of these to 0, and I would set this guy to 1 and him to 0. Again, if I add everything along the bottom, what am I going to get? Well, I have 1, 2, and I have nothing, anything else, so the value is 2. So now let's get a little bit more fancy. Let's say I wanted to represent the value 5. So the value 5, I'd set all of these to 0, so these are all 0. I would need 1, 4. This guy would be 0, and I would need 1, 1. So this right here would represent the value 5, because if I come through here and I add everybody up that has a 1 in it, we get our final result. In this case, I have 1, 4 plus I have 1, 1 equals the value 5. Excellent. We're finally starting to look at memory at a very low level, dealing with our little bits, 1s and 0s. All right, so now that we see how that works, let's see if we can apply that to some of our predefined types. Now, what I'm going to do is I'm going to start out with let's do integer types, because we've all looked at integers. What's an integer? It's a whole number, right? Has no decimals in it. Positive and negative? Maybe not always. We'll see that in just a second. So integer. So this will be integer types. All right, so let's go ahead and write a few things down, just hopefully to make life a little bit easier. We're going to make a name section, if I can spell name, and I'm going to draw a line that's just going to kind of cut all the way across here, and let's just do something like this. So we'll have a name section, a description section, and then finally a range section. I'll leave a little bit of room on the end in case I want to write some notes down. All right, so the range is going to be presented in basically our min and max of what can be stored in that area. All right, so let's go ahead and start out with, instead of starting out with int, everybody has seen int. Let's work our way up to it. Let's start out with something really small. So the smallest thing that we have of an integer type is going to be a signed byte. So let's go ahead and write it down. So it's going to be an SBYTE. Ooh, a signed byte. Now, how do we use this? Well, all of these different types, we use them just as we've seen before with declaring any kind of variable. Let's say I wanted to create a signed byte whose variable name was I. I could just simply do this in code. SBYTE I terminator. Or I could even initialize it right there by saying equals 5. And that's completely legit. Now, here's where things are going to get interesting. What is a signed byte? It is an 8-bit signed integer. At this point, I'm hoping everybody's starting to understand why I introduced you to bits and bytes. Because now you know that a bit, our very lowest area of storing any sort of information, a 1 or a 0, here we have a signed byte, requires 8 bits. What can it hold? Well, it can hold the following range. Negative 128 to 127. That's kind of odd. And let's go ahead and look at it another way as well, using some exponents over here. Basically, negative 2 to the 7th power up to a positive 2 to the 7th power minus the result of that, minus 1. All right, Buzz, this just blew my mind. This looks extremely confusing. How do you get this? Well, quite simple. See the little example I did right here? I did this example for a reason. You could say right now that this is I. I is an 8-bit memory location. It is holding a signed byte. I put a 5 in it. So what you're seeing right now is, just stipulate once again that these are all zeros. And you're now looking at the ones and zeros that's being stored in that memory location. Right, Logan?
Right, actual binary memory.
There you go. So that is a signed byte that I just created. Well, how did we come up with this negative 128, if we go in the negative direction, to a positive 127? Because if there's a 1 in this position right there, well, I already know that my value, if everything else is 0, but there's a 1 right there in 128, if I add it all together, I'm going to have a value of 128. Now you see where the word signed comes in. We are using this guy right here. This is our signed bit, if you will. This is what is letting us know that the number is negative. Okay? Now, what does that mean? Well, if this value in here is a 0, we're looking at a positive number. And everything else down here, if we come in here and add it all up, if you want to pull out your calculator and add all of these numbers up, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 will give you 127. Very interesting, eh? Now, take 2 to the power of 7. Well, we already figured it out for you. There's 2 to the power of 7, and we showed you that's 128, and subtract 1 from it. What value do you get? 128 minus 1 is 127. There you go. So that's where that number actually comes from. Now, negative 128. Well, quite simple. If instead of having a 0 over here, we have a 1. And let's stipulate that everybody else over here is 0. The way this will be treated is this 1 is saying this is going to be negative. And what position is it in? 128. So it is a negative 128. And look at this. Our minimum range right here is negative 2 to the 7th power. Again, we've already figured it up for you. 2 to the 7th power is 128. Negative, so it'd be negative 128. There is where we physically get that from. Does this help make it clear, Logan, in your opinion, on exactly how we're getting these minimum and maximum ranges?
Most certainly. It comes down to what you had said earlier on storing how much data. And this shows the reason that we have different amounts of memory that we use to store different data types. Because you had written in the description that this is an 8-bit signed integer. 8-bit is what we've got drawn here. We have 8 individual bits that are used to represent this value.
Exactly.
Now we only have 8 of them. That means we can't go more than 128 in any direction because we can't represent more than, well, in this case, if you want to look at the range, say that's 255 values throughout, that means with 8 bits, that is the highest number of discrete values that can be represented. That is every combination of 1 and 0 throughout 8 bits.
Exactly. So in this case, with a signed byte, you can have negative 128 to a positive 127. That is all that will fit in there. Now, the next type. So let's see how this applies as we continue through the different predefined value types. The next one is going to be a short. All right, what exactly is a short? Now, I'm not going to draw these out, but the same principles that I demonstrated with the signed byte will apply here. And you're going to see real quickly why I'm not going to draw this out. This is a 16-bit. So a 16-bit signed integer. That means, once again, it goes positive and negative. Now, what is the range? Now, I'm not going to draw this out. In fact, let me go ahead and give myself just a little bit more room right here. There we go. And there we go. I will draw this one out, but after this, I'm only going to use exponents only. So, because the numbers are going to get way too huge. So here we can go negative 32,768 to a positive 32,760, check it out, 7, one less. So what does this look like? Basically, we're saying we can go minus 2 to the 15th, so that's negative 2 to the 15th power, to positive 2 to the 15th power minus 1. Now, some of you may be sitting there thinking, oh, my math skills are rusty. Oh, that looks so scary. Oh, come on, pull out a calculator. Figure this up. You know, if I drew out 2 of these bytes, okay, so once again, I've drawn all of these guys in here for you, right? But this is only 8 bits. So if I drew out 2 of these and continued on with the very next bit after 2 to the 7th being 2 to the 8th, 2 to the 9th, 2 to the 10th, and continued on down from there and worked out the math the exact same way that we did down here on the bottom, you apply the exact same principles. Whatever numbers are in there, you just add all of those values up all the way across, and you will come up with, you'll find that if you put a 1 in the very far left and everything else is 0, then that's going to indicate that it is going to be a negative number because this is signed, and it's going to be a negative 32,768. Now, if that bit way over here, okay, because remember, we now have 2 of these, so we're just stipulating right now that I drew 2 of these. If that very first bit over here is a 0 and the next one is a 1, then what are we going to have? Well, we're going to have basically 1 less. So it's how you want to, well, we could take that 1 away and populate all the rest with a value of 1.
Right, the other 15 lower bits
are all a 1, exactly. Then you add all of those up, and then you're going to get this right here, 32,767. So again, every single one of these set to a 1, and the last one is a 0. And then if you want to add 1 to it, all of these toggle to 0, and this guy toggles to a value of 1. But since it's signed, it indicates that it's negative. So this is how we come up with this range. We can now hold a much larger number now, but it's because we're dealing with double the amount of memory. Well, why is this important, Buzz? You might be asking that if you're completely new still to the world of programming. Simple. When you start defining your data types, you can start thinking about what kind of value am I going to hold in here? I'm only going to be holding the value, 1 to 15. All right, well, if that's all that is ever going to go in there, do you necessarily need to use something like an integer, which can hold a really, really huge number? Do you see what I'm getting at?
Right, because if you have something like how many days there are in a week or something like that, you don't need 32,000 discrete values to hold that.
No.
8 bits would be plenty.
Exactly. In fact, in this range here, it's even bigger than 32,000 with going negative 32,000 and going positive 32,000. Now we've got 65,000 some odd combinations. Whew. All right, so hopefully this is starting to become a little bit more clear while we've got these different types. So let's go ahead and move on. The next one is one that you have seen over and over and over. It is the lovely integer, an int. And once again, let's come over here with the description. It is a 32-bit. Once again, it is a signed integer. Now, what value does it hold? It's big. So big that I'm not going to write it out. I'm just going to come over here and put in a negative 2 to the 31st power to a positive 2 to the 31st power minus 1. Again, the math will apply exactly the same as demonstrated above with the bits. So moving on from there, the next type we have is a long. So for whatever reason, let's say I'm going to be dealing with a very large number that's not going to fit in an int, but it is of integer type, meaning that it's a whole number. I can come in here and create a long. So a long. And a long holds, here we go, ladies and gentlemen, the big 64-bit. And again, it's a signed integer. Whew. Now, what does it look like? Oh, stand back. It is a negative 2 to the 63rd. From there going to a 2 to the 63rd minus 1. Yeah, you have a good time drawing that out, because I'm not going to do it because it's going to take up this entire page. The bottom line is this. The number that holds is huge. So if you need, for whatever reason, some just gigantous integer value, then a long just might be the answer for you. And now this is going to wrap up all of our different signed integer types. Now let's take a look at our different unsigned types. Unsigned? What does that mean? Well, what if you know that, like days of the week, as Logan was saying earlier, you're not going to have a negative days of the week. So perhaps you don't want to go in there and use a signed integer. So let's go ahead and see if we can clean this up just a little bit, Logan, by drawing a line across there, like that. I'll move this back over here just in case I need that other space for whatever reason. And we shall start out with a byte. Ah, see the similarities? We have a byte, and we had a signed byte. That means we're moving back to the world of 16-bit data storage. I mean 8. 8 is what I mean. That's what I get when I'm looking all over the place and writing and talking. So 8-bit, and this time around it is an unsigned. Well, I like how fast you were to catch me right there. Shut up. All right, unsigned integer. I know you've got my back. All right, so what does this mean? This means, now since we're dealing with real small numbers again, now I can go in here and write these out, that the lowest end would be 0. We can also bring our attention back up here because I can use this now to demonstrate this. So here is a 0. Notice how they are all zeros, okay? Now, if I was to set every one of these to a value of 1, since this is indeed an unsigned integer, this means that we cannot go negative. This means this 1 right here would count as a value of 128, plus 64, plus 32, if all of these were set to 1, plus 16, plus 8, plus 4, plus 2, plus 1, gives us the amazing total of 255. Okay, so that is our range there. And again, what does this look like? Well, our math is just a little bit different here. It goes from 0 up to 2 to the power of 8 minus 1. Okay, think about the way this works. So if we were able to go one more bit over, that would be to the power of 8, which would give us 256, minus 1 gives us 255. Okay, pretty clear, Logan?
Another thing you can look at is in the case of the signed byte, you have 128 values in the negative and 127 in the positive. That added together gives you your 255.
That's correct. Absolutely. All right, so let's go ahead and undo that little mark and move on to our next one. Hopefully at this point this is becoming super clear to everyone. So what other kind of predefined integer value types are available to us? Well, we also have the unsigned short. And the unsigned short is a 16-bit unsigned integer. And its range is 0 to, and I kind of gave hint to it when we were talking about the negative 32,000 to 32,000, it is 0 to 65,535. So there's that value. And what does this look like? 0 to 2 to the 16th minus 1. Simple enough. All right, moving on from there, we also have an unsigned int, just in case we need a large integer value that we know will not be going negative. And this is going to be a 32-bit unsigned integer. And once again, we're starting to deal with some very big numbers, so I'm just going to simply put that it runs from 0 up to 2 to the 32nd power minus 1. A much bigger number than the 16-bit. All right, now moving on from there, our final one is going to be an unsigned long, so it is going to be a U long, like such, and it will hold, of course, a 64-bit. This is holding just such a huge number. So unsigned integer. And again, its range is going to be 0 up to 2 to the 64th power. That is a 4, I promise you. Minus 1. There you go. Well, Logan, that pretty much shows them all of the integer value types that are predefined and available to us in C#. So just go in there. You need to create one of these. You can simply say int space I, and you've just declared an integer, and the variable name is I. If you need an unsigned short, you could say uShort space I, and you've just declared an unsigned short integer. Okay? So that is our integer types. So now let's go ahead and move on to the world of decimals. And let's see, how do I want to draw this out? I think I can squeeze. Yeah, I can. That's why we have the ability to do that. Yes. All right, so let's go ahead and come over here and draw a little line. And just keep in mind that at this point what we're talking about is floating. So floating point types. And I can, if you give me just a second, bear with me, I can come over here and extend this down just a little bit. Good enough. And now, with floating point types, what are we looking at? Well, we've all seen the float. What does the float give us? All right, this is where stuff just gets crazy, okay? It gives us a 32-bit single precision floating, so I'm just going to say floating point number, okay? Wow, what does that mean it holds? Well, it holds approximately 1.5 times 10 to the negative 45 power to approximately 3.4 times 10 to the 38. What does it mean? Well, it means pretty big, basically. It basically means that we have a precision to 7 digits out. Now, what if we need something with even more precision than that? Well, what we can do is turn our attention to a double. This is where things really do get big. This is going to be a 64-bit double precision. So double precision floating point number. And we're going to be dealing with approximately 5.0 times 10 to the negative, prepare yourself here, ladies and gentlemen, 324th power to approximately 1.7 times 10 to the 308th power. Small number, eh, Logan?
Just a bit, yeah.
I mean, we're talking 10 to the 308th. That's huge! All right, so what kind of precision are we dealing with here? Well, we were dealing with 7 significant figures right here, and we're dealing with between 15 and 16 here. So you can see where if we're dealing with some sort of scientific calculation that needs to be calculated way out after the decimal point, that we would perhaps want to use a double. Big stuff. Very big stuff. But what if I want to deal with a tightly controlled decimal number? What does that mean? Logan, do you want to spend just a second and talk about how dealing with floats and doubles aren't necessarily tightly controlled?
Right. Well, you see from the example here that we've described these as approximate values. It doesn't mean it contains exactly from this level to another one. It's approximate. What that means is you can't always rely on the exact value of a floating point. As a matter of fact, you generally don't want to do a specific equality check against one float, because depending on the processor and probably other factors, you have what are known as floating point errors.
Right.
That means the number 0.1 could technically be 0.0999 to some really long number, which as far as a game is concerned, or as far as a visual effect is concerned, would look like 1.
Right.
But as far as math is concerned, is not 1. And therefore, if you did your equality check, you wouldn't come up with a value of 1, and therefore would have a bad check. Now, what a decimal would do is it would give you a decimal number where you could rely on all of the significant figures. If you typed in the number 0.01, you could rely on the fact that it was going to be exactly 0.01, and you could check it against 0.01, and you could be guaranteed that that check would come out correctly.
And Logan just gave it away, the decimal types. Let's go ahead and throw that in real quick. Why is this so important? Well, think about what Logan just said. Using those floating point errors, let's say we were writing some sort of financial application. Do we really want those floating point errors introduced? That's just a real loose example. Perhaps you'd want to use a decimal type, and this will give us, well, exactly what we asked for. So it is defined as a decimal. All right, it is a 128-bit high precision decimal notation number. All right, and it is a plus minus 1.0 to 10 to the negative 28 to a 7.9 times 10 to the 28. Okay, that is its range. All right, there you go. Now we have just worked our way through, I believe, that's all of the different number types that we're going to be dealing with. But again, these are predefined value types offered to us with the C# language. So you've seen integer types, you've seen floating point types, and you have seen the decimal type. From there, we're going to talk about a couple other types that you have already seen, and that will wrap up the whole slew of value types that are predefined for us. So let's see, how do I want to do this? Bear with me for a second. I'll just come over here, and let's create one of these, and then I can just turn that off, and that'll work. So the next one that I want to talk about is going to be the Boolean type. So and the Boolean type is actually quite simple. Let me go ahead and just fill out an area here for me to write some of these things down. So the Boolean type, let's do this. Name, and we'll say description or value that's in here. All right, so a Boolean type is a bool, and it holds a true or a false. I mean, this is what it holds. This is what you check for when you are checking against a bool. Okay, you're checking against true or false. Now, and again, we've used this too. We've used bools several times in Volume 1. The next type is going to be a character type. So let's see, how do I want to write this? We'll just do it like this. And that is going to be a char. Did we mention char all the way back in Volume 1? Maybe. Maybe not.
Maybe very lightly.
So what does this represent? It is a single 16-bit Unicode character. So it's a unicharacter that we're holding in there, 16-bit.
Right, and I imagine you could load up the char map, look at the Unicode side of the char map, and that's the kinds of values you'd be storing. You'd be storing a value that would reference that specific character.
Exactly. And from there, let's see. Whoa, what do you know? Well, that brings us to an end of all of our predefined value types. So let me do this. So again, this end of predefined, there's the key word again, value types. Is right here. All right, now we're going to talk about predefined reference types, and we're only going to talk about this for just a second. So predefined reference types. Now there are a lot of predefined reference types when you really start digging down into it inside of C#, because of our, the whole foundation that's available to us, right?
Right, when you get into all the classes available to you, there is an immense library.
It's like over 24 or 2,500 different things available to us there. But here we go. Let's talk about two very simple ones. Object and string. And we've all used string, right? Now, what is an object? Well, object is basically, it's our root type. All types in the CTS derive from object. Okay, so we can just say that this is our root type right here. And to be honest with you, at this point, this is all I want to talk about until we come back and visit variables again, and we introduce a few more kind of interesting and powerful concepts where we're going to bring object into it. But right now, there's our predefined reference types. We're just going to throw out two of them, object and string. And we all have seen that a string holds, alphanumeric text. Hello, world. I just had to go there, didn't I? There you go. That's something that's being held inside a string, but it is a reference type. What is a reference type again? That means inside your variable, it is holding a reference to the actual object that is holding the data within. Okay? And we'll talk about that a lot more in the next video. So looking at my notes here, Logan, I believe that is everything that I wanted to talk about in this video. Once again, this video was covering predefined value types and a couple of the predefined reference types. Is there anything you'd like to add to this?
Not really. I think that takes care of it.
Okay, so with that, that is going to wrap up this video. Thanks a lot.